So in our reaction mechanism video, we'll be discussing the acid catalyzed addition of an alcohol to an alkene. So in step 1 of this reaction, we see the interaction between sulfuric acid and methanol. So methanol, like all other alcohols, has a pK value of between 15 to 16, while sulfuric acid is a very strong acid, and the loss of the first proton there is going to be closer to -9. So here we see methanol, the oxygen atom specifically, acting as the nucleophile in this case to capture this proton on the sulfuric acid. Then, because this hydrogen can't have two bonds, the 2 electrons localized within this OH bond are actually transferred directly onto the oxygen atom. In this case, you see a negatively charged sulfuric acid compound and a protonated methanol structure. So this reaction proceeds in the forward direction, in this case because of the pK value. So sulfuric acid is such a strong acid that it wants to lose its first proton. However, it is important to note that all of the reactions, each step of each reaction in this case is reversible because of the acid-base chemistry going on. So then in step 2, we see this alkene acting as the nucleophile. So it is going to attack this hydrogen in this protonated methanol structure, and then because, again, as we mentioned, the hydrogen cannot have 2 bonds, this bond will break and actually transfer its electrons directly onto the oxygen. So the result here is a neutral methanol structure that we actually began with. And then in this case, we have the formation of the carbocation. So this is the rate limiting or rate determining step in the reaction, the formation of the carbocation. And in this case, we have a secondary carbocation forming. So we could have added either here or here, added a hydrogen atom. So here we added the hydrogen atom here in accordance with Markovnikov's rule because we wanted to create the most stable carbocation. So in this case, between a primary and secondary carbocation, we added the hydrogen here in order to make or produce the most stable possible carbocation, which is the secondary carbocation. And here we have no opportunity for a hydride or methyl shift, so we know that we can proceed knowing that we have the most stable carbocation possible in this example. So here we now see methanol interact with this charged structure. So the oxygen atom here is going to again behave as a nucleophile and attack this electrophilic structure because this is an electron poor zone that wants more electrons. So in this case, it proceeds forward. This compound actually attaches onto the hydrocarbon chain here. So we see the oxygen actually bonding directly to this carbon. And the result is an oxygen atom with 3 bonds and 1 lone pair. So that actually has a positive formal charge. So then, in order to remove that positive formal charge, we do see that methanol, which is present as a solvent in this system, this oxygen atom will again behave as the nucleophile, attacking this proton, and then because hydrogen can't have 2 bonds, it will break this OH bond to transfer those 2 electrons directly onto the oxygen atom. In this case, we see the regeneration of this protonated methanol structure and our final product, which is an ether in this case. So here, our final organic products are the 2 enantiomers of this final ether. So we can see that this carbon-oxygen bond could be added either from above or below, and that's represented by the wedge and dash racemic enantiomer structures in this example. So thank you so much for watching our video.